So far in this waves unit, we've been looking at properties and how to calculate them for waves, but also specific examples pertaining to sound. In this video, we're going to extend that focus to light and also talk about the electromagnetic spectrum and all the different types of waves that are included within that. To start us off, let's make a comparison between sound and light. When we talked about sound and we said you are changing the frequency of your sound, we were really referring to the pitch. That if you change the frequency, you are changing musical notes because every note, every pitch has a different frequency to it. In light, if we're talking about visible light, changing the frequency of the light is going to change the color of that light. That a red light has a lower frequency than a violet or purple light. We're going to talk more details about this because color doesn't make sense if you're talking about other electromagnetic waves. But within the visible part of the spectrum, pitch and color are analogous. So that means that if you are looking at light and you have the frequency, you can describe any color in this visible light spectrum by its frequency or its wavelength in nanometers. So here, if I wanted to see a red light with a nanometer, or the wavelength of red light, we'd find that at 650 nanometers. Blue light would be something more like 450 nanometers. We can also convert this into a frequency as long as we know the speed. In a vacuum, all electromagnetic waves, including light, travel at 299,792,458 meters per second. Now that is an incredibly precise measurement, way more precise than we're going to need in this class. So whenever we're going to be using the speed of light, we're going to round that to 3 significant digits. That's 3.00 times 10 to the 8th meters per second. That is an incredibly important number that we're going to be used throughout this entire year, really. For the speed of light, or the speed of an electromagnetic wave, we give it a special symbol, lowercase c. This is actually the same c in E equals mc squared, Einstein's famous equation, but c represents the speed of light specifically, rather than v being just a generalized velocity. And the speed of light is provided to you in your data booklet for the IB Physics exam. That shows up here, speed of light in a vacuum c is 3.00 times 10 to the 8th meters per second. So we can use that to solve some interesting problems. The other day, we looked at sound and how sound is not instantaneous, but we kind of treated light like it was instantaneous. Light isn't instantaneous either. It's just we don't really have a distance scale that it matters. But if you go out into space, things are far enough apart that it does start to matter. The sun is about 150 million kilometers away from Earth. So we can actually figure out how long it takes light to travel that. It is not instantaneous. We can use our velocity equation, velocity is distance divided by time, and solve that for time. Time is just distance divided by velocity. Our distance in meters is about 150 billion meters, divided by our speed of light, which is 3.0 times 10 to the 8th meters per second. We can calculate how many seconds and ultimately how many minutes it takes the sunlight to get to Earth. Solving this through here, I find that that's about 500 seconds, 499 seconds, which equates to about 8.3 minutes. Which means that if for whatever reason the sun were to stop shining right now, and we were looking at the sun, not directly of course, it would take 8.3 minutes before you realize that the sun wasn't there anymore, because the sunlight that we are seeing is the light that escaped the sun 8.3 minutes ago. That's how long it took to take that journey. So our light equation is going to operate the same as our wave speed equation. The speed is equal to frequency times wavelength. For light or electromagnetic waves, we just swap in a c for v, because that c is governed by the laws of nature. And this idea of light is just one part of a larger picture. This is the electromagnetic spectrum. Notice how visible light is just one tiny aspect of this. We have also radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays that are also part of that spectrum. And to be clear, there isn't a whole lot different about the wave itself, besides the fact that its frequency and wavelength have changed. They are moving at the same speed. It's very similar to sound, that you can increase your sound beyond your range of hearing. If you have a higher sound than you can hear, that goes into a category that we call ultrasound. And you've probably heard of ultrasound before. It's used in medical procedures as a way of seeing inside the body. You could also go below the range of hearing, and we call that infrasound. Well, here, there is light that exists beyond our range of seeing. We just call it visible light because that's what humans have evolved to see. An electromagnetic wave is made out of two oscillating fields of electric field and magnetic field. And notice that these are oscillating perpendicular to the direction of the wave travel. So we've talked about transverse and longitudinal waves. Which one of these would it fall under if it was perpendicular to the direction of travel? When we saw sound, sound was parallel to the direction of travel. That was a longitudinal wave. Light, electromagnetic waves, will operate as a transverse wave. And that'll become more important when we get into polarization and those sorts of things. But for now, know that this picture here is representing a transverse wave. And we can also have standing waves within this idea of an electromagnetic wave, just like we did with sound. A microwave oven works on the same principle as a resonating sound in a tube. We have a standing wave that is operating there. And because of that, we can actually use a microwave to calculate what the spacing is between hot spots here. Because if it is a standing wave, that means there's some areas with really high vibration, high amplitude, and some areas that are nodes that don't vibrate at all. In those nodes, the food doesn't cook. So on my microwave here, I noticed that it had written on it the frequency of the microwave that it was using. It was 2,450 megahertz. I know that the speed of light is 3.0 times 10 to the 8th. So I can plug that in to solve for the wavelength of this microwave. 3.00 times 10 to the 8th divided by 2,450 megahertz. Mega is just a prefix for million. So we're going to multiply that by 10 to the 6th to get that into hertz. That comes out to 0.12 meters. That is the distance of one wavelength of this. But that is not the distance between antinodes or between nodes. Between antinodes or nodes, that would be half of that distance. So we can take that divided by 2 and find that 0.06 meters is the spacing between hot spots or cold spots in this microwave, which equates to about 6 centimeters. I was curious if this was true. So I took this microwave and I bought a tin of Crazy Aaron's thinking putty that is thermally activated. What it's designed for is you play with it in your hand, and when you hold it, the heat of your hand causes it to change colors. Well, the same thing happens if you put it in a microwave and heat it up that way. So I covered a plate with this, and then I made it so that the turntable was deactivated. So it wasn't going to rotate through and evenly heat that putty. And what I found was there were very clear hot spots and cold spots. That the yellow is where the antinodes were, and heated up that putty and caused it to change colors. I took a ruler and I measured that from one antinode to another, and I could do it between some others as well. But I found that that was 6 centimeters, which is exactly what we calculated using the speed of light. So finding the standing waves in a microwave allows us to tangentially talk about the speed of light there as well. All right, now let's focus a little bit more on the overall spectrum here, the fact that it's more than just light. We experience several parts of the spectrum from signals from space, whether that is a wave coming from a nearby star or satellites. Sometimes, though, there are waves that get filtered out by our atmosphere. So while we talk about all of them, we have experience with all of them, at least coming from sources on Earth, and not all of them make it through the atmosphere to come to us from space, which is a good thing. Gamma rays are the highest energy of these waves, which means they are the shortest wavelength. They have a wavelength of about 1 picometer, which is 10 to the minus 12. We see gamma rays in high energy sources out in space. but in order to see them, we need a satellite because they get filtered out by our atmosphere. We also see gamma rays in nuclear radiation, and that is where we'll talk about it most in this class, in our nuclear unit. Our next most energetic form of wave is an X-ray. You probably have experience with X-rays at some point. Maybe you went to the dentist or the doctor to get an X-ray taken so we can see the bones. An X-ray is just a high energy wave that is able to travel through parts of our skin, but is blocked by bone. So really all an X-ray image is it's just a shadow. Same as if I were to cast a shadow of my hand using visible light, I would see an outline of my hand. With an X-ray, what I'm seeing is an outline of the bone. This is just an inverse, is a photo negative of that to make the black turn into white so we can see those bones more clearly. An X-ray has a wavelength of 10 nanometers, which is 10 to the minus 10 meters. Next, we're getting into light that we experience more on a daily basis. Ultraviolet light. The primary source of UV light is from our sun for us. And UV light can be designated in a couple different ranges as well: UVA, UVB, and UVC. UVC is primarily blocked by our atmosphere, but UVA and UVB make it through. If you look on the back of a sunscreen container, you will actually see it talk about UVA and UVB rays and which ones, or a single one, it blocks. UVB has a longer wave, which causes tanning. UVA is a shorter or even longer wave that penetrates deep, and can really cause some damage there as well. So these high energy rays can cause damage because they have so much energy to them. There are some other examples of UV light as well that we have man-made here on Earth. One application that you've probably also experienced ultraviolet light is in black lights. If you've ever been like cosmic bowling before and you've seen the black lights that are on the wall, these black lights, they glow to our eyes in kind of this purplish light. They're not black at all. The reason that they're purple is because purple is the closest color to ultraviolet in that visible light spectrum. So part of that light is going to be a little bit purple because these are right on that border. Now, something about ultraviolet light that is important is it is a higher energy light than visible light is, which means when it strikes something, usually when it's white or light colored, is actually exciting some of the electrons inside that material. And when those electrons fall back down, they are emitting their own light, which is why my white bow tie here is glowing very strongly. My teeth are glowing. Really anything that's white. Here in my workshop, you can see a variety of different things on my workbench are also glowing white in the presence of this black light. The next most energetic form of wave is visible light. Now we are to the part of the lights, our electromagnetic spectrum, that we can sense with our eyes. And as I mentioned earlier, the frequency and wavelength affect the color of light that we see. That's how we're interpreting the different colors. This is one of my favorite animations of all time. This shows the different wavelength and frequency of these different colored lights. Red there has the longest wavelength and the smallest frequency. It bounces less often than the others, versus blue has much higher energy, shorter frequency, or higher frequency and shorter wavelength there. Which means that if you have seen like a red laser has a lot of energy because it's very focused, but it is the lowest energy of laser light that you can have for a given amount of wattage, given power. The next highest, or one of the more energetic forms of laser is a green laser, like this one here, which has enough energy to light a match. So in that example, the green laser light has enough energy to transfer and actually get that match started. I also have a purple laser Uh, you can kind of see it there in the camera. Purple light has even more energy than green light. This isn't as powerful of a laser, but the light itself has enough energy to make things glow in the dark. If it's something that already glows in the dark, this can excite the parts of that glow in the dark material that cause it to glow. So here's a video of me using my purple laser to make my glow in the dark skeleton start to glow in some cool patterns. An easy way to remember where these different colors fall on this amount of frequency is to think about what's on either side of visible light in the electromagnetic spectrum. We just talked about ultraviolet light. Ultraviolet light has more energy, enough energy to damage your skin and create a sunburn. Violet is the closest to ultraviolet. So it's just under the ultraviolet, that high energy form. On the other side, we have red, and just under red is something called infrared. Now, infrared has a couple of pretty interesting applications. The first of which, the one that you've probably heard of more often, is as use in like thermal imaging, that we are all glowing right now. You are glowing in a wavelength that can't be seen by your eye because they fall outside that visible light spectrum. You are glowing in the infrared. We'll talk later on in the thermal physics part of this year about things like a toaster. If you look at the coils on a toaster, they start to heat up and glow in the visible part of the spectrum because they get so hot. But right now, you're not hot enough to glow visibly, but you are glowing in the infrared. Using a special camera with special sensors, we can actually see this happening.
If I take these two glasses of water, they look pretty much identical in every way. They're both very clear, and they're both just normal water. And in the visible part of the spectrum, that's true, that these are exactly the same. But as you can see in the infrared, there's a clear difference between these two. This one on this side is significantly hotter than this one over here. And we can see the difference because of the different wavelengths that are being emitted from the hot versus the cold or room temperature.
So we can see how infrared and heat can be connected, but it doesn't have to be heat. You're actually surrounded by infrared LEDs all over the place. So here are a couple of examples of infrared LEDs being used to transmit information. There are many different devices that use infrared light to transmit information. So one example is a simple remote. So you might have a remote at home that looks like this, and you'll see that there's a little LED on the end of it. And if you push a button and you look at that LED, you're not going to see anything because this LED is not emitting visible light. Instead, this is emitting light in the infrared part of the spectrum. Now, some cameras, like the Android phone that I'm using right now, actually don't filter out all of the invisible infrared light and allow you to see that light. And if you take that remote while pushing any button looking at that LED, you'll see that it will start to flash. Now here, that color that you're seeing doesn't really mean anything in particular. With my eyes, I don't see anything coming out of that LED. Instead, this is just the camera's filter not filtering out that wavelength. You'll see that it's pulsing. Now the pulsing is just transmitting information in ones and zeros in this wavelength that you're not able to see, but the receiver on the other end can sense that. Some products use infrared light in order to let you see in the dark. So this isn't using like thermal infrared like we were seeing in that infrared camera. Instead, it's using infrared LEDs like the one that we saw in the remote. This is a baby monitor that allows you to see your child even if it's dark in the room. And the way it works is there's this circle of LEDs that right now don't look like anything because those LEDs are emitting infrared light. So we're going to actually turn off the lights here to activate those infrared lights so that you can see what's going on. So with the lights on, you don't see anything in particular because the camera is set to use that visible light in order for the camera to work. But if I turn off the lights, you'll see that those infrared lights start to glow. They turn on, and again, my camera is able to see it because it's not filtering out that infrared part of the spectrum, but my eyes don't see anything.
To my eyes, basically, that camera is just in the dark.
So as you can see, infrared lights are all around us, and as you can also see, apparently infrared causes my hair to grow even longer. Those videos were from another time. Let's move on to the next form of electromagnetic waves, and that is microwaves. If you stretch out those wavelengths even longer, that is the microwave wavelength that we were talking about earlier with those standing waves. This is also the portion of the electromagnetic wave spectrum that captures Wi-Fi. So if you're watching this on a device right now that is streaming the internet from Wi-Fi, it is actually using electromagnetic waves in the microwave part of the spectrum to transmit that data. Other forms of data transmission are commonly used with radio waves. That's where you stretch out the wavelength even farther, and most examples of data transmission over especially long distances are in radio waves, because radio waves can travel further and aren't blocked as easily by things. So radio stations as well as TV stations that are streamed over the air. The United States has a frequency allocations chart that sections off different frequencies for use in different ways. And it's pretty interesting to see some of these parts of the chart here, that you'll see that, for example, FM radio has, it might be hard to see in the video, but 88 to 108. Those are megahertz. And those are specifically the frequencies of the wavelength that it's being transmitted at. You might have a car radio that you turn the dial to a certain radio station, and chances are you know that radio station by a number, and that number is somewhere between 88 and 108. All right, you should be able to name these relative to each other in terms of frequency and wavelength. Our longest wavelength is radio, then microwave, then infrared, visible, ultraviolet, X-rays, and gamma. It is important to be able to rank these because they carry with them the amount of energy associated with how high or low of a frequency it has. So the highest energy waves are gamma rays down here. The lowest are radio waves. So the main takeaways in this video is you should be able to identify and use speed of light to solve problems with wave equations. You should be able to estimate the wavelength magnitude for different electromagnetic waves, know how they are related to each other, and provide some real-world examples of each of those electromagnetic waves like we did here in this video.